So the next talk will be given by Arya Mazumdar from UCSD, who's going to give us millions of information about quantum.
Thanks a lot for that introduction, and thanks for the organizer. Thanks to the organizer to let me speak. I was wondering whether this is a theory talk. I guess it's an applied talk now that I'm speaking in this workshop. So this is about one-bit compressed sensing. It's a work jointly done with two students, Nami Matsumoto and Shomobroto Pal. Shomobroto graduated some time back, and Nami is still a student in UC San Diego. So this is about one-bit compressed sensing. So many of you probably know about the compressed sensing problem. Let me just reintroduce it over here. So this is like some image or signal over here, which looks high dimensional, but is actually sparse because there are there are not too many edges or so on. So when we try to capture such things, such signals, then we use sensors, that's some resource, to capture all the pixels in this image. And then we store it, at which time we also compress. So we acquire all the signals, but then by compressing, we are throwing out most of it. So the compressed sensing paradigm is where we combine the sensing and compression together and do this in one shot. So that usually is done by a linear operations, which is sort of standard. So you assume X to be this high dimensional signal, so N is pretty large. But we assume that this signal is actually sparse. I write it by this L0 norm. That means there are only at most K non-zero coefficient, although this is a high dimensional vector. We can relax it by saying that they're approximately sparse, or it is sparse in some other basis, such as Fourier basis or wavelet basis. So what we are doing is multiplying X by some matrix, which is also called a sampler in some literature, or this is called taking measurement or taking sketches. So you multiply X by A. This is an M by N matrix, and M is assumed to be much smaller than N, so that you get the compression, right? And you get some Y, which is M dimensional, which is A times X, right? So in compressed sensing, now the main problem is to design a matrix, which is the measurement matrix, with small number of rows, means you get more compression. And we also need an efficient recovery method so that we can reconstruct X up to certain level, right? So that was the compressed sensing problem. It is still a pretty active area of research. There has been hardware built to accommodate this type of paradigms, right? So what is one-bit compressed sensing? It is this phenomenon that we are again taking the sketches or samples, which is inner product between rows of the matrix A, which we are writing it as AI. But then we are just interested in taking one bit of information from there. So we are just keeping the sign of this number, right? The sign is binary. It can be +1 or -1. For some notational reason, I'm writing 1 and 0. So sign of our number is 1 if it is greater than 0, and it is 0 if it is less than equal to 0. And so this is why is this interesting? It is because we have digital systems, so we need to do quantization at some level. So even when we are acquiring these real signals by multiplying with some matrix, we then have to quantize, right? So and this is some sort of extreme quantization where we are quantizing them to just 1 bit. There is also this, compressed sensing is sort of sparse linear regression. It's pretty well studied. But if you introduce this type of nonlinearity, it doesn't know what happens to the recovery process. So it's interesting because it's some sort of, again, extreme nonlinearity. So it's both extreme quantization and extremely nonlinear. It falls under some broad class called generalized linear model or single index model, which are extremely well studied in statistics. It's also related to the half space problems or sparse half space problem in learning theory. So one thing to notice in this one-bit compressed sensing problem is that you cannot really recover X because you're only getting finite number of bits, right? So, and for example, if you just scale X by anything else, right, any number, this is not preserving that scale. By sign, you're still getting, so you can never really recover the norm. You lose those information. So What do we mean when we say recovery in one-bit compressed sensing? That usually goes in two directions. So one is this approximate vector recovery, which is an area where I worked on the most. So this is basically saying, suppose x is unit norm and you want to only recover the direction of x, right? So approximately recover it. So it's called approximate vector recovery. It has a lot of connection to some topics in statistical machine learning, like perceptron and half spaces. On the other hand, you can, yes.
I don't know what the physics of where the measurement process comes from, but is it possible to observe the sign of ax plus b? Like, can I compare it to something and then decide?
It is possible. It is possible, and like there might be even measurement. So in signal processing, you can have this noise inside of the quantization sometime, and they add this. It's called this dithering.
Right, but if you can compare yourself to different thresholds,
that is also possible. I don't think it is a very difficult hardware. If you can implement this with 0, you can implement it with other thresholds.
But then it's too many bits. More than one bit, then you do if you do that.
Yeah, that's why.
Okay.
You can generalize these things.
Yes.
The other thing that you can do is support recovery, where you are just giving me the support of x. Right? So that's a finite amount of information. So now you don't have to worry about the scaling or anything else. And support recovery is pretty interesting by itself, because when you are looking at applications of this in classification, this actually exactly correspond to feature selection in machine learning. And sometimes in signal processing, you can recover the support and then just assume a uniform distribution on the support, or a power law distribution in the support, and see how well you are doing the signal recovery, right? So this is more combinatorial, this support recovery problem, and this is what we are going to talk about today. So we are going to formalize this, but there are very interesting problems in approximate vector recovery. Okay, so let's formalize the support recovery problem now. So you have this y equals to sine ax, and you know that there is some sparsity constant. Let's just assume that x is exactly like at most k sparse. So there are at most k non-zero entries. So you want to minimize the number of measurements, that is the number of rows in A, and you want to come up with an efficient recovery algorithm that gives you a set of coordinates. This I is a set of coordinate. Ideally, what you want is that this I to be exactly equal to the support of x. So that's the support recovery problem. And then now the question is, what is the number of measurements that you need, and what is a recovery algorithm for this? Right? Okay. So one special case that you can think of is when the matrix A is binary. Sorry, I should have written m by n. It's like this is a typo, it's written only n. But if A is binary, and if it is known that the vector x is also binary, then these measurements are exactly what are called the group testing measurements, right? Because and that is the reason I have defined the sign to be 1 and 0 instead of 1 and -1, so that I can show this correspondence between group testing and one-bit compressed sensing. Okay, so in this special case, this is exactly group testing, and then throughout this talk, we will see that this comparison, this parallels to group testing is coming up again and again. Okay. Now, what is known? So it is known. So by this from this paper by Acharya, Bhattacharya, and Kamath in 2017, it is known that it is necessary to have at least k square over log k log n. So we are not going to care too much about this log term. So about k square measurements.
The amount of information you get one bit out, but where they are is, specify where they are.
For the support, yes, exactly. So that we need to specify the k out of the n support.
It's not going to just be the support, it's going to be the small thing support times log n or something.
So that's why I have this log n's appearing in this. Right? It's not, you cannot do it with just order of k. So one other thing I should mention, that I'm looking at the non-adaptive version of the problem. You can pose it in an adaptive way, where you are choosing the rows of A, like one step at a time. Well, you can look at all the previous measurements, But here I'm just saying that you have A in one shot, and this is, so non-adaptivity is one thing. Another thing is the universality. You want one matrix to work for all sparse vector. For each time you are not selecting a new A matrix. Right? So these are the two key concepts. With those constraints, this is what is known, that you need at least this order of k square rows with this log terms. And it is also sufficient to have order of k square log n rows of A. Right? There is an efficient algorithm that is order of n, that runs in time order of n, that actually going to give you this. Now, if you are aware of the literature of non-adaptive group testing, these are exactly the bounds in group testing as well when you wanted to do exact recovery. And this is also for exact recovery in 1-bit compressed sensing. Right? So one thing to note is that information theoretically, or what Rudy was saying, we would always assume that it would take something like order of k log n measurements, because that's sort of the information theoretic bound to identify k out of n coordinate. But because of this non-adaptivity and universality, we are losing that we have this extra factor of k, and we cannot really, there is not much, we cannot, there is a lower bound which is only log k factor away. So it looks like the price of adaptivity or universality is too steep over here.
What does universality mean?
Universality means that this one matrix is going to work for all sparse vector.
So, right.
So what is the solution of this in group testing? So in group testing, you have a similar situation where the price of non-adaptivity and universality is too steep. So what do? They say that we are going to decode with some amount of false positives. So that means we are going to include some of the elements, coordinates in the support, which can be wrong. And we are just going to bound that number of wrong coordinates to something small. Right? So that we call superset recovery. Instead of that exact support, we are recovering the superset. By the way, if let me know when that I'm not keeping track of time and at all. So, so you are going to return a set which is which is at most this size, whatever is the size of the actual support of x times 1 plus epsilon, right? And the support is totally included in S. So the reason we go for superset is that like false positives are sometimes allowable. Like if you are doing the application of feature selection, you want to know all important features. It's fine if you include some of the non-important features as important, rather than to exclude some of the some of the important features. So false positives are good. The price of false positive and false negatives are different, right? Then similar with group testing, right? If you think of infectious disease and all those things, so it's fine if you actually do some false positive, but false negative might have a hefty price where you are basically releasing an infected person in the community. Right. So by doing this type of relaxation in group testing, you can maintain non-adaptivity, you can maintain universality, and come back to this order of k log n. Now the question is whether you can do the same thing in 1-bit compressed sensing, and this you can do via something called list disjunct matrix that I will come to shortly. And I have about 10 minutes, I was told. So then, okay. So one thing to notice over here is that since I am just interested in order of reconstruction, like this sign measurement over here is actually giving me a ternary measurement. It can tell me where this entry z is exactly equal to 0. How? Because I can just repeat this measurement with ai replaced with minus ai, right? If in both time I'm getting a 0 measurements, then I know that whatever is the argument of the sign is exactly equal to 0. So I can actually tell 0 from non-zero apart with this type of measurements. Okay, great. But there is some very important difference from group testing, is that when there is a 0 measurement in group testing, I can actually tell that the support of these two vectors that I am measuring against, the pool and the signal, they are disjoint. The supports are disjoint when I have a 0 measurement in group testing. In 1-bit compressed sensing, a 0 measurement can mean that they are just orthogonal. Their support do not have to be disjoint. Okay? So for example, if you look at in these two vectors, their support actually have a pretty large overlap, right? So they have large overlap over here. But if you just take the inner product of this with this, you will get a 0. Therefore, even if you can identify the 0 measurements, you cannot really tell that these two measurements have disjoint support, because and that was crucial in group testing. So one solution is for each of these measurements, I keep k linearly independent measurements for. So I basically just, so for in lieu of this one measurement, I have k different measurement vector, which are all linearly independent. That will do the job. So I can convert any group testing scheme to 1-bit compressed sensing, but that will have a k-fold increase in measurements. So we don't really want that. So what is the remedy of this? It's something that this paper by Acharya et al. Came up with. This is to use this thing called robust union-free families. And they have some certain nice properties. So what happens is you have this set family, B1 up to Bn. They're all subsets of this 1 to M, and they are of fixed size. So you can think of this as columns of the matrix A. Okay. And now if you take any k plus 1 columns, then the intersection between, so this is basically whatever a union of k columns are covering of the one column left, and that is bounded by d over 2. So it's not like k, so any k columns are not covering entirely some other column, right? There is a pretty big slack. So if you have this property, then you can use directly these matrices for 1-bit compressed sensing by using this very simple algorithm. So you will just look at the y, which is the measurement vector, support of that, and see the intersection with the columns of the A matrix, right? If the intersection is bigger than d over 2, then you will include it in your support, otherwise you will not do it. And it's pretty straightforward to see that this works, okay? This works, and this will then, your problem is being reduced to constructing this this robust union-free families, and that you can do with order of k square log n. So that was that paper. So now we want to do superset recovery, and in group testing we had a similar construction called disjunct matrices, and the extension that you need for superset recovery is called list disjunct matrices. So here we had robust union-free families. What we want now is a list union-free family. Okay. Okay. So that we tried. I can show you the definition in the next slide. It turns out that the exact recovery argument that we had in the last slide that do not really generalize. That do not generalize because there is some strong separation property that is being lost over here. So this is the list union-free family. So what we are basically saying that instead of just one set, if you take two sets of size L and K, then you take you just isolate out one column and look at the union of all other columns. It's not covering it well. So that's the list union-free families. So there is an example of how this is the list disjunct thing that you need in group testing, where you look at this one column, it has one coordinate that is missing in all of the union of any other columns. Here for the case of list union free, you have at least two. So that's why this is called list union free. Turns out that this is not sufficient. And just in the interest of time, I cannot give you much intuition about why this is not sufficient, but we may ended up making a conjecture that binary matrices will not be able to do the job for this. Okay, so we need something else. So what eventually worked is this observation that we can still try to use this list union-free matrices and use the same algorithm, right? With a little tweak at the end. I'm not going to go over the algorithm. It is again exactly the same as before, and there is some small thing that we do. And what we ended up getting is approximate recovery, which is not a superset. That means we have both false positive and false negative. Right? So that we can guarantee just by using this. Okay, so by using list union free. So why we were insisting on superset recovery, I said that again, like false positives might be less risky than false negatives. So we still aim to get only false positive, but at least we have something, approximate recovery. Then, so with binary matrices, we can get to this, and apparently this meets the information theoretic bounds for approximate recovery. So what ended up working is to take a list for superset recovery or recovery with only false positive is we take the matrix, the list union free matrices, and then we scale each of the entries with some numbers that are algebraically independent. So just to over the rationals. So again, this is happening because of some technical reason. We can show that this. Okay, probably I don't have how much time do I have? 2 minutes. Okay, so here is what the algorithm is, and I will see if there. So the algorithm is first just do the usual thing, right? So that's the approximate what worked for approximate recovery. You were just looking at the intersection between support. If that is small, you are just going to. If that is large, you are going to include it. If it is small, you are not including it. And approximate recovery done at this stage. So now at this stage, you have both false positive and false negatives. Then you do a cleanup stage in the algorithm. You basically look at look at each of the columns, and then you look at the union of the support and support of the measurement plus all of the columns that were already in that approximate recovery step, right? And if that is big, you include it. Right, so this step cleans up the false negatives, and you have superset recovery. So what we can show that this algebraic independence that we insisted upon, that ends up taking care. If you remember what algebraic independence is, this. So if you have this coefficient, these numbers would not satisfy any polynomial equation where the coefficients are coming from the rationals. So that will actually guarantee that you do not have any of these zero measurements by doing these cleanup steps. Okay, so that's a bit technical, and I don't have time to go into that. Unfortunately, this doesn't work for any epsilon. It works only when epsilon. Remember, I have epsilon k false positive, right? So as long as the number of false positive is not more than square root of k, it works. So what ends up happening is that while in group testing, I have this, by allowing for false positive, I get order of k over epsilon. So this epsilon proportion of false positive, k over epsilon log n. In 1-bit compressed sensing, by using list union free plus this algebraic independence, I get k, the max of k over epsilon log n and k to the power 3 over 2 log n. So it's still a reduction from k square, which was the case for exact recovery, but I cannot really go to k over epsilon, which is the information theoretic limit, except for some regime. Okay, so there are some, so these are the upper and lower bound, you'll find it in the paper, so I'm not going to go with the, but if you assume some other property, so if it were rational, if instead of real vectors, if you have rational vectors, then you can actually close this gap with the construction that I mentioned. So there is something special about between real and rational that's actually not working over here. There are some other way, if x were binary, or if x were, the dynamic range or something were bounded, you can get to information. Like for those special classes, you can get to information theoretic limits. Okay, so I think that's all I had to say. I think it is possible. Like all of us, and I think Nami and Shomabhata, they also think it is possible to break this 3 over 2 barrier, this k to the power 3 over 2 barrier, but we don't know how to do it. It's like you're invited to work on this, and thanks all.
Maybe 1 or 2 questions.
So it's usually quantized, right, those numbers. So these are rational.
Yeah, so for all practical purposes, we solved the problem. If you think that this x is just coming from some rational, then this is fine.
But does the cost, I mean, not the asymptotic, but the real cost depend on the quantization precision?
Not really. As long as these are rational, I should be fine. The thing is that I can write all these rationals as p over q for some large p and whatever p and q, and then if I take this algebraically independent number, I can choose them with this list union free matrices, so that if you know when there is this zero measurements which are actually not with non-zero intersection, when that happens, it ends up being that they satisfy some polynomial equation which I have forbidden because I have chosen algebraically independent number. So for the case of reals, that do not happen. And yeah. So only when this epsilon is less than 1 over square root of k, I can make it happen by doing some tricks.
Yeah. So, I mean, as far as I know, and I could be wrong, but like algebraic independence would mean, like, for example, a transcendental number is.
No, not all. Like it depends. Like they have to be together. Like so. This entire set of numbers, they have to be algebraic. Like one, yeah. So suppose something like pi or square root of pi. So this is algebraically independent by itself, but it is not algebraically independent if you have more variables. Yeah. So the end. What?
Even more restrictive then. I mean,
right, it's very restrictive, but you can find them, right? So those algebraically independent number, you can find them. Yes.
it's easy to find this.
Yeah. Yeah.
Random sampling kind of thing.
Yeah. The thing is that for rationals it is effectively solved, and we cannot really sample a real number. So the problem is effectively solved, except for this gap between rationals and reals. So, yeah, but that's like a thing that will bug. I mean, just for theoretical reason, I guess. So in that way, the talk is applied, because I think the interesting thing remains only in theory.
So for 0-1 matrices, it's still open, or
if you insist on the matrix to be binary, but your signal x can be anything. I think you can show some lower bound for binary matrices. It will not be. Yeah. I don't
and
think.
maybe also.
But I don't think it is solved.
Okay.
It's somewhere. Yeah. So I think there is this other interesting problem where the vector x is binary, but you can choose the A matrix to be anything else. So there, for exact recovery, you also have this k to the power 3 over 2, but you don't have order of k. So there is no lower bound. Like the upper bound is k to the power 3 over 2, lower bound is order of k, and then there is this gap. So just for binary x, and not like, and whatever you can choose A in whatever.
Okay, thank you.
Thank you.
Should we take a poll for that? So I think it would be nice to take